Hello and welcome. I'm Gianluca Malato, and in this video we are going to uncover a simple but powerful idea why the median is often more trustworthy than the mean when you want to summarize real data. On the slide you can already see our main character, a skewed distribution, where the mean is dragged toward the long tail, while the median stays closer to where most observations actually lie. That's the core problem we'll tackle. When does the average you're used to hearing about fail to represent a typical value, and when does the median give you a clearer picture? By the end of this video, you will know exactly what the median is in practical terms, how to compute it for different kinds of datasets, and most importantly, when you should trust the median more than the mean, especially with messy, real-world data like incomes, house prices, or waiting times. Let's get started. Now let's see a concrete example of how the mean can mislead us. On this slide we have 5 people and their incomes. 4 of them earn moderate, fairly similar amounts. And one person, however, earns an extremely high income. You can see that as the very tall bar on the right. Notice the 2 horizontal lines across the bars. The blue line is the mean income. It's pushed upward, closer to the rich outlier than to the rest of the group. If you only looked at this mean, you might think everyone here is doing quite well, which is clearly not true. The red line is the median income. It lies right in the middle of the moderate incomes, where most people actually are. It ignores how extreme that top income is and focuses on the central person in the group. So, looking at this picture, ask yourself, which number better reflects reality here? The mean dominated by that single rich outlier, or the median sitting among the typical people? On this slide, we'll pin down a clear, intuitive definition of the median. The median is the middle value of an ordered dataset. There are 2 key ideas hidden in that short sentence. First, you must order your data from smallest to largest. Imagine placing each observation as a dot on this horizontal number line, from left to right. Once they are ordered, you can meaningfully talk about what a middle means. Second, the median splits your data into 2 equal halves. The highlighted red point in the center of the line is the median. To its left you have 50% of the data. To its right you have the other 50%. It doesn't matter how big or small the extreme values are, only their position in this order list matters. When we talk about an entire population, we often describe the median as the 50th percentile or the second quartile, the point below which half of all observations fall. Now let's walk through how to calculate the median when we have an odd number of observations. On the slide you see our 7 data points, 2, 5, 7, 9, 10, 13 and 15. Step 1. Sort data from smallest to largest. In this example they are already sorted. Step 2. Count how many values you have. Here n equals 7. Step 3. Find the position of the middle value. For an odd number of observations we use the formula n plus 1 divided by 2. So 7 plus 1 / 2 equals 4. The median will be the 4th value in the order list. Step 4. Look at the 4th value in the column of numbers. Counting from the top, 2 is first, 5 is second, 7 is third, and 9 is fourth. That highlighted 9 is the median. Notice that there are 3 values below 9 and 3 values above 9. This matches our definition. The median splits the data into 2 equal halves. On this slide we'll see how to calculate the median when we have an even number of observations. Our dataset is 2, 5, 7, 9, 10, 13, 15, and 20. Step 1. Sort data from smallest to largest. Here they are already sorted. Step 2. Count how many values you have. In this case, n equals 8. Step 3. Because 8 is an even number, there is no single value exactly in the middle, Instead, we find the two middle positions, n divided by 2, which is the fourth position, and n divided by 2 plus 1, which is the fifth position. In our order list, these are 9 and 10, highlighted on the slide. Step 4. To get a single median value, we take the average of these two middle numbers, 9 plus 10 divided by 2, which equals 9.5. So, for an even number of observations, the median is the average of the two central values. Here, the median is 9.5. On this slide, we bring the mean and the median together and compare how they behave. First, a quick reminder. The mean is what most people call the average. You add up all the values and divide by how many there are. Because it uses every value, it is sensitive to any extreme points in the data. The median instead is simply the middle value once the data are ordered. It only cares about rank and position, not about how large the extremes are. Look at the left distribution. It's symmetric, like a bell. Here the mean and the median sit on top of each other at the center. In this kind of balanced situation, both give a very similar summary. Now look at the right skewed distribution with a long tail to the right. The mean in blue is pulled toward that tail. The median in red stays near the bulk of the observations, where most data points actually lie. This is why the median often describes a typical value better when data are skewed. Now let's see why the median is called a robust measure of central tendency. On the left, you see our original small dataset, plotted as bars. The blue horizontal line is the mean, and the red line is the median. With all values in a reasonable range, mean and median are quite close. On the right, we keep the first 5 values exactly the same, but we push just one value up to an extreme level, turning it into a clear outlier. Watch what happens. The blue mean line jumps upward, following that single extreme bar. The red median line, instead, hardly moves at all. As long as fewer than half of the observations become extreme, the median barely changes, because it depends only on order, not on how large those extremes are. This is what robustness means: resistance to distortion by outliers. In real-world, messy data measurement errors, data entry mistakes, very heavy tail distributions. This robustness is crucial. The median still describes a typical value, while the mean can be completely hijacked by a few extreme points. On this slide you can see 4 real-world situations where the median gives a clearer picture than the mean. First, income and wealth. In many countries, a small number of very rich people pull the mean income up. The median income instead sits right where the typical person is in the distribution, so it's much more representative. Second, house prices. A few luxury properties can be extremely expensive. If you average all prices, those mentions distort the result. The median home price focuses on the middle of the market and better reflects what most buyers actually face. Third, waiting times and delays. Think about call centers, hospitals, or flights. Most waits may be moderate, but a few rare, very long delays can make the mean explode. The median waiting time is much more stable over time. Finally, performance metrics in data science. Measures like median absolute error or median response time are preferred when you want robust evaluation. They are less affected by a handful of bad cases or outliers. On this slide, let's turn everything we've learned into simple practical rules. On the left, under mean, you see when the mean is a good choice. Use the mean when your data are roughly symmetric without heavy outliers, and when every single value really matters. This is common with the physical measurements, lab results, or well-controlled experiments, where extreme values are rare and usually meaningful. On the right, under median, you see when the median is more appropriate. Choose the median when your data are clearly skewed, when outliers are present, or when you care about a typical value. That's the case for incomes, house prices, social or behavioral data, and many operational metrics with occasional extreme values. Notice the central reminder: you don't have to pick only one and forget the other. A good analyst checks both mean and median, and most importantly looks at the entire distribution plots, histograms, percentiles, before drawing conclusions. Let's wrap up with the key ideas. First, the median is the middle value of an ordered dataset. It splits your data so that half the observations are below it and half are above it. Second, unlike the mean, the median is often more robust. It barely moves when you have outliers or strong skew, so it usually gives a better sense of a typical value in messy data. Third, that makes the median essential in statistics, data science, and data analysis, especially with real-world data like incomes, prices, and waiting times. If this video helped you, please like it, subscribe to the channel, and leave a comment with your questions or topics you'd like to see next. And if you want to practice statistics with real exercises in Python, check out my book Statistics with Python. 100 solve exercises for data analysis. Inside you'll find the step-by-step exercises on probability, hypothesis testing, correlation, regression, and statistical analysis using Python. You'll find the link in the description.